video review number 4, which is good old L'Hopital. L'Hopital's rule limits involving ing indeterminate forms. And in particular, 0 over 0 or infinity over infinity. A couple of quick examples from pre-calculus. X goes to -5, and we've got x plus 5, and we've got x cubed plus 125. Direct substitution, if you put -5 here and here, you would see you get 0 over 0, which is not the answer. So we're going to change this limit problem using L'Hopital into another limit problem. X still goes to -5, but now we're going to take derivatives, and we're going to take the derivative of this denominator and put it there. Well, the derivative of x plus 5 is 1. And we're going to take the derivative of the numerator, and the derivative of x cubed plus 125 is 3x squared. And then we're going to put -5 into this limit, and so we get 3 times -5 squared, which is 75. And if that limit exists, that's also the answer to this original problem. Okay, rather trivial. Let's look at one that's a little bit more exciting. So we have the limit as x goes to 0, and we're going to have the natural log of x plus 1, and we're going to have the sine of 3x. The sine of 3x. Okay, so direct substitution, again, always start that way. Put 0 into both of these, and you would get sine of 3 times 0, and the natural log of 0 plus 1. Well, 0 over 0, that's not the answer. So let's try L'Hopital. Write L'Hopital above this, and then a new limit. Limit still x goes to 0. And I guess we should be, no, we're okay. X goes to 0. I was going to say this might be a one-sided limit, but I think these are well defined for x's. Remember, the log of x looks like that, but the log of x plus 1 would be a shift left 1. So the asymptote would be over here. So that's well defined, around 0 anyway. This says x is getting close to 0. And the sine certainly well defined. So anyway, we get 3 times the cosine of 3x, and we get 1 over x plus 1, right? The derivative of, again, just think derivatives. We are not using the quotient rule here. The derivative of the log, which we had on a previous video, and the derivative of the sine, which we had in a previous chapter. So we get that, and now we try plugging 0 into this guy, and we get 3 times the cosine of 0, and then 1 over 0 plus 1. So the cosine of 0 is 1. This is 3 over 1, which is 3. Okay, so there's a second example. Let's do one that involves infinity. So scroll down here, and let's try the limit as x goes to 0. This one will come in from the right, and you'll see why in just a second. Let's suppose we have 1 over x, and we have the natural log of x. So if you think about the behavior of both of these, the 1 over x graph goes that way and like that. And as x goes towards 0 from the right, this red graph becomes infinitely large, right? And the natural log graph we already looked at. The natural log graph looks like this. And as x goes towards 0 from the right, this log graph goes down, negative infinity. Well, that's not the answer. So infinity over infinity, or negative infinity over infinity, or any of that sort says use L'Hopital. So we're going to do L'Hopital's rule here, and we're going to write equals L'Hopital here. So now we still have the limit, we still have x going towards 0 from the right, and we take a couple of derivatives. This one becomes 1 over x, and the one up top, the derivative of 1 over x, is negative 1 over x squared, right? So let's clean that up algebraically. We have x going towards 0 from the right, and we have negative 1 over x squared times x over 1, right? Dividing by a fraction, invert and multiply. So this is the limit as x goes to 0 from the right, and we cancel, and we get negative 1 over x. Negative 1 over x. And as x goes towards 0, this becomes extremely, extremely large negative, so negative infinity. You could just try putting some numbers in there. You know, if x was 1/10, this would be negative 1 over 1/10, which is negative 10. If x was 1/100th, this would be negative 1 over 1/100th, right? 1 over 100. And that becomes negative 100. So yeah, sure enough, this limit does not exist. So back to the original problem, this limit does not exist, non-existing limit. Okay, let's do an infinity over infinity where it actually does exist. So we'll try that. And again, this is a pre-calculus problem. So the limit as x goes, let's go out to infinity now, and we'll have x minus 3x squared over x squared plus 2x plus 1. So you might remember on pre-calculus how this plays out. We do have the same exponent here and here. The highest power is the same. So we're really just looking at the ratio of leading coefficients, negative 3 and 1. So this answer should be negative 3. Negative 3 over 1. Yeah, we said leading coefficients. This first, function here, isn't the leading coefficient 1? Well, no, it isn't. You normally would write this in decreasing powers. So if we did write it as x gets really big, negative 3x squared plus x over 1x squared plus 2x plus 1. Yeah, you can see the, quote, leading coefficients. That's going to be the answer. Now let's pretend we forgot all our pre-calculus, but we do know L'Hopital's rule. So L'Hopital's rule would allow us to do this because this, in fact, is infinity over infinity. Okay, actually, I guess this would be negative infinity over infinity. Right, negative infinity over infinity. This is infinitely large here as x gets big, and this is infinitely large. The lower powers become less and less relevant. So let's try good old L'Hopital. L'Hopital. So limit as x gets big, I take the derivative of the top, negative 6x. Take the derivative of the bottom, 2x plus 2. Still infinity over infinity. So use L'Hopital again. And we have the limit as x gets really big. The derivative of the top is negative 6. And the derivative of the bottom is 2. Well, that's a constant. Doesn't matter what x is. This is always going to be negative 3. And that's our original limit, negative 3. Okay, so yeah, anything 0 over 0 or infinity over infinity, use L'Hopital. If you have other indeterminate forms like 1 to the infinity or 0 to the 0, you do have to do some other stuff. Those might be bonus questions on the test. You generally don't even see these in May. So there were some problems in the problem sets that dealt with other forms. I guess, the traditional one, the one that is most likely to be seen would be x gets really big, and we have 1 plus 1 over x raised to the x power. And if you just think x is getting really, really large here, this expression becomes closer and closer to 1. We have 1 plus 1 over x. And the exponent is obviously big, so it looks like 1 to the infinity power. But that's not the answer. Okay, the answer, The answer is, if you remember, E. And I did that derivation in class. Again, not on the test, probably not in May. So there's L'Hopital. Congratulations, Emily, on your production, and hopefully see you tomorrow.